In the frozen vacuum of space, a lone observer floats in absolute darkness. Around them, nothing. No stars pierce the void. No galaxies glow in the distance. Just endless, perfect blackness stretching in every direction. They've been waiting here for longer than numbers can express, watching the universe die. And now, finally, they see it. A single point of light in the infinite dark. The last object in existence. A supermassive black hole billions of times more massive than our sun, glowing faintly as it reaches the final moments of its incomprehensibly long life. For 10 to the power of 100 years, this black hole has been the only thing left, the only structure, the only complexity, the only meaning in a cosmos that has become perfectly, utterly empty. The observer watches as the black hole begins to shrink. Faster now, the glow intensifies, brighter, hotter. The temperature rises to billions of degrees, then trillions. In its final microsecond, the black hole radiates more energy than a trillion suns. And then, with a flash that no one else will ever see, it's gone. The observer is now surrounded by absolute nothing. Photons stretched to wavelengths larger than galaxies. A universe at maximum entropy. A temperature so close to absolute zero that the difference is meaningless. And nothing will ever happen again. Not in a billion years. Not in a trillion. Not ever. This is the heat death of the universe. And you're about to witness how we got here. Right now, as you watch this, the universe is more alive than it will ever be again. This is the Golden Age, the brightest era in all of cosmic history. Stars blaze across the heavens. Galaxies spiral in elegant formations. Planets orbit their suns. Life exists on at least one world, maybe millions. This moment, right now, is as good as it gets, because everything you see, everything you know, everything that exists is slowly, inevitably, permanently dying. The universe is 13.8 billion years old. That sounds ancient. It sounds like we're living in the twilight of existence. But we're not. We're barely past the beginning. If the universe's entire lifespan were compressed into a single 24-hour day, we're living in the first second after midnight. Everything that comes after stretches into incomprehensible eternities of darkness and cold. The stars will die. The galaxies will disperse. Matter itself will decay. And eventually, the universe will reach a state where nothing can ever happen again. Not because there's no space or time, but because there's no energy left to make anything occur. This isn't speculation. This is physics. The same laws that power your phone and light your home guarantee this ending. Entropy always increases. Energy spreads out. Everything becomes more disordered. Always, without exception. The universe is winding down like a clock that can never be rewound. And scientists have calculated exactly how long it will take. Let me paint you a picture of the universe today. Our Milky Way galaxy contains approximately 400 billion stars. That number doubled recently when we discovered our galaxy is twice as large as we thought. 400 billion suns, each one a nuclear furnace converting hydrogen into helium and releasing unimaginable amounts of energy. Some of these stars are red dwarfs, tiny and dim, burning their fuel so slowly they'll last for trillions of years. Others are blue giants, massive and brilliant, living fast and dying young in spectacular supernova explosions. Between the stars float clouds of gas and dust, nebulae where new stars are being born right now. Stellar nurseries where gravity pulls matter together until it ignites in nuclear fusion. This process is happening in thousands of locations across our galaxy at this very moment. new stars flickering to life, and our galaxy is just one of trillions. The observable universe contains roughly 2 trillion galaxies, each one home to hundreds of billions of stars. Do the math, and you get a number so large it becomes meaningless. 10 to the power of 24 stars. A trillion suns blazing simultaneously. These galaxies aren't randomly scattered. They're organized into vast structures called the cosmic web. Filaments of dark matter spanning hundreds of millions of light years, connecting galaxy clusters like neural pathways in a cosmic brain. Between these filaments lie cosmic voids, regions of space with almost nothing in them. The universe has structure, order, complexity, for now. But there's something else happening, something that changes everything. The universe is expanding, not just growing, but accelerating. Galaxies are moving away from each other faster and faster. Space itself is stretching, pulling everything apart. This acceleration is driven by dark energy, a mysterious force that makes up 68% of everything in existence. We don't know what dark energy is. We can't see it, can't touch it, can't directly detect it. But we can measure its effects. And those effects are terrifying. Dark energy creates a kind of anti-gravity. Instead of pulling things together like normal gravity, it pushes space apart. The more space you have, the more dark energy exists to push it apart even faster. This creates a runaway process. More expansion creates more dark energy, creates more expansion. The universe isn't just growing, it's accelerating towards maximum expansion. Galaxies that we can see today will eventually move away from us so fast that their light can never reach us. They'll cross a cosmic horizon and disappear from view forever. In a sense, the observable universe is shrinking even as the actual universe expands. Future astronomers living billions of years from now will see a very different sky. Darker, emptier, lonelier. Here's something even more disturbing. Star formation is already slowing down. The universe reached peak star production about 10 billion years ago. We're already on the downward slope. The reason is simple. Stars are made from gas, primarily hydrogen. The universe has a finite amount of gas, and we're using it up. Every star that forms locks away hydrogen in nuclear fusion. Some of that hydrogen gets recycled when stars die and explode, enriching space with heavier elements. But much of it gets locked away permanently in white dwarfs, neutron stars, and black holes. The universe is running out of raw materials. In the early universe, gas was everywhere. Thick clouds of hydrogen filling space, ready to collapse into stars. Now, billions of years later, much of that gas has been used. What remains is spread thinner by cosmic expansion. It's harder for gravity to pull together enough material to ignite a new star. Star formation rates have dropped by 97% since the universe's peak, and they'll continue dropping. Eventually, not a single new star will form anywhere in the cosmos. The last stellar nurseries will go quiet. The final generation of stars will ignite. And then, nothing. Just the slow death of existing stars over trillions of years. The lights are going out. Not all at once, but one by one. The universe is becoming darker. Let me take you on a journey into the future. Jump forward 100 billion years from today. Earth is long gone, vaporized when our sun swelled into a red giant about 5 billion years from now. But that's a minor detail in the cosmic story. The real change is what you'd see if you looked up at the night sky. Most of the galaxies we can observe today have disappeared. Not destroyed, but moved beyond the cosmic horizon. Space has been expanding for 100 billion years, accelerating the entire time. Distant galaxies have been carried away so fast that light leaving them now will never reach us. The Milky Way's view of the universe has shrunk dramatically. Future astronomers in our galaxy would see only the local group: the Milky Way, Andromeda, Triangulum, and a few dozen dwarf galaxies. That's it. The rest of the universe, all those trillions of galaxies, have been swept beyond an invisible boundary. As far as these future astronomers could tell, the universe consists of a small cluster of galaxies surrounded by infinite empty space. They'd have no evidence that anything else ever existed. They'd have no way to discover the Big Bang. The cosmic microwave background radiation, that faint afterglow of creation that we can detect today, will have been redshifted to wavelengths longer than the observable universe itself, effectively undetectable. Future scientists might conclude they live in a small, eternal, unchanging cosmos. They'd be completely wrong, but they'd have no way to know it. The universe's own expansion will erase the evidence of its origins. But something dramatic will have happened much sooner. In about 4 billion years, the Andromeda Galaxy will collide with the Milky Way. When I say collide, I don't mean the galaxies will crash like solid objects. Stars are so far apart that actual collisions between them are incredibly rare. But the gravitational interaction between two galaxies containing hundreds of billions of stars creates chaos. Stars will be flung out into intergalactic space. Others will have their orbits completely rearranged. Gas clouds in both galaxies will compress, triggering intense bursts of star formation. The night sky, if anyone is around to see it, will be spectacular. Andromeda will grow larger and larger over millions of years, eventually filling half the visible sky. Then the galaxies will pass through each other, tidal forces pulling long streamers of stars out in both directions. They'll orbit around each other several times, each pass stripping away more material. Eventually, after about 1 billion years, the two galaxies will merge completely. The result will be a giant elliptical galaxy astronomers have already nicknamed Milkomeda. No more elegant spiral arms. Just a football-shaped blob of roughly 800 billion stars orbiting in random directions. The supermassive black holes at the centers of both galaxies, Sagittarius A star from the Milky Way, and Andromeda's even larger central black hole, will spiral toward each other and merge. This collision will release gravitational waves so powerful they could be detected across the universe, if anyone is still looking. Milkomeda will be one of the last great galaxies. After this, no more major galaxy formation will occur in our region of space. The show is over. Now jump much farther into the future, 100 trillion years from now. This is approximately 1,000 times longer than the current age of the universe. In this distant era, something unprecedented happens. The last conventional star forms. Somewhere in the cosmos, in a galaxy whose name we'll never know, gravity pulls together the final cloud of hydrogen gas with enough mass to ignite fusion. A small red dwarf, probably. These miserly stars are the most common type and the longest lived. This final star flickers to life, begins burning its hydrogen fuel, and settles into a stable existence that will last for trillions of years. But it's alone. No other stars are forming, anywhere, in the entire observable universe. The era of star formation, which began just a few 100 million years after the Big Bang and lasted for over 100 trillion years, has finally ended. Astronomers call this the end of the stelliferous era, the age of stars. What comes next has a more ominous name: the degenerate era, an age dominated by the corpses of dead stars, white dwarfs cooling slowly in the darkness, neutron stars spinning down, black holes growing fat on the remnants of everything that falls into them. The universe is transitioning from a place of light and life to a vast graveyard. The stars that still exist will continue burning for a long time. Our sun, if it were still around, would have already died and become a white dwarf. But red dwarfs, those tiny dim stars that sip their fuel carefully, will continue shining. The smallest red dwarfs can last for 10 trillion years. Some will survive even longer. These will be the last natural sources of light in the universe. Imagine the loneliness. A single red dwarf, deep red and faint, sitting in a galaxy that's otherwise completely dark. No other stars nearby. Just dead remnants and darkness in every direction. This star is using up the last of its hydrogen, fusion reactions slowing, output dropping year by year. Eventually, even this final star will exhaust its fuel. The core will contract one last time, squeeze out the final fusion reactions, and then stop. No explosion, no supernova, just a gradual dimming. From red to infrared to nothing. The star will become a black dwarf, a theoretical object that's never been observed because the universe isn't old enough yet for any to exist. A cold, dark sphere about the size of Earth, containing the mass of a star, radiating no energy, just floating through space, inert, dead. And with that final star going dark, the age of natural light in the universe ends forever. What I'm about to tell you will happen. Not might happen, not possibly happen, but will happen with absolute certainty. We're going to watch the complete death of everything. Every star in every galaxy will burn out. Every planet will freeze or be destroyed. Every atom in existence will face an uncertain future. Black holes, those seemingly eternal monsters, will evaporate into nothing. The universe will reach a state of maximum entropy where nothing interesting can ever occur again. And we know exactly how long each stage will take. We know when the last star will die. We know when matter itself will decay. We know when the final black hole will evaporate. The numbers are so large they break human intuition. 10 to the power of 40 years. 10 to the power of 100 years. Numbers so vast that if you tried to count to them, one number per second, you'd need more time than the universe has existed, multiplied by itself billions of times. But we're going to travel through this timeline together. We're going to watch the universe die. Slowly, inevitably, completely. And at the end, we're going to identify the very last thing that will exist before everything becomes nothing. The final survivor in a dead cosmos. Are you ready? Because once you understand this, once you truly comprehend the fate that awaits everything, you can't unknow it. The universe is dying. It's been dying since the moment it was born. And we're living in the brief, beautiful moment before the long darkness begins. We've arrived at 10 trillion years into the future. Think about that number, 10 trillion. If you counted one number per second, it would take you 310,000 years just to count to 10 trillion. The universe today is only 13.8 billion years old. We've jumped forward in time by a factor of almost 1,000. And in this distant era, something final is happening. The last red dwarf stars are dying. These tiny, dim stars have been the universe's most resilient survivors. While massive blue giants burned out billions of years ago, while sun-like stars exhausted their fuel and became white dwarfs, the red dwarfs kept going. They're the misers of the cosmos, burning hydrogen so slowly and efficiently that they can last 1,000 times longer than our sun. But even misers eventually run out of money. The final red dwarfs are now exhausting the last of their hydrogen fuel. Watch what happens. The fusion reactions in the core begin to sputter. The energy output drops. The star's outer layers cool from red to deep red to infrared. There's no explosion, no dramatic finale, just a slow, inexorable fade. The star dims gradually over millions of years until finally the last fusion reaction occurs. A single hydrogen nucleus fuses with another, releasing one final burst of energy. And then silence. The star is now a black dwarf, a cold, inert sphere of carbon and oxygen floating through space. With this final death, the stelliferous era ends. For the first time since a few 100 million years after the Big Bang, no stars shine anywhere in the universe. Not a single nuclear furnace burns. The age of light is over. Take inventory of what remains. The universe is now a graveyard filled with stellar corpses. White dwarfs are everywhere, the remnants of stars like our sun. These objects are roughly the size of Earth, but contain about half the mass of the sun. That's a density so extreme that a teaspoon of white dwarf material would weigh about 15 tons. They're not producing energy anymore, just slowly radiating away the leftover heat from their formation. When they first form, white dwarfs are scorching hot over 100,000 degrees Celsius. But with no fusion to generate new heat, they can only cool down. This cooling process takes an absurdly long time. A white dwarf will take trillions of years to cool from white-hot to red-hot. Then trillions more to cool from red to black. The universe we're in now, at 10 trillion years, is just starting to see the first white dwarfs transition to black dwarfs. These are purely theoretical objects. No black dwarf has ever been observed because the universe hasn't been around long enough for any to exist yet. But here, in the deep future, they're becoming common. Dark spheres drifting through space, invisible except for how their gravity bends light from even more distant objects. Then there are the neutron stars, remnants of stars that were too massive to become white dwarfs, but not quite massive enough to collapse into black holes. These objects are even more extreme. A neutron star packs about 1.4 times the sun's mass into a sphere just 20 kilometers across. That's roughly the size of a city. The density is so extreme that a teaspoon would weigh as much as Mount Everest. Neutrons, the particles that normally exist in atomic nuclei, are crushed together so tightly they touch. It's matter at the edge of what physics allows. And of course, there are black holes. Scattered throughout space are stellar mass black holes, the corpses of the most massive stars. These monsters formed when stars weighing 20, 30, 50 times the sun's mass could no longer support themselves and collapsed catastrophically. Now they sit in space, invisible, detectable only by how their gravity affects anything that comes near. But something strange is happening to those white dwarfs as they cool. Deep in their cores, a transformation is taking place. White dwarfs are made primarily of carbon and oxygen, the ashes of the helium fusion that occurred when these stars were still alive. At the temperatures and pressures inside a cooling white dwarf, these atoms begin to arrange themselves into a crystalline structure. The star is literally solidifying. First, the core crystallizes, forming a lattice of carbon atoms locked in perfect geometric formation. Then, the crystallization front moves outward. Over billions of years, the entire star transforms from a hot gas into a solid object. And what's carbon in a crystalline structure? diamond. The white dwarfs are becoming cosmic diamonds, Earth-sized spheres of pure crystal floating through space. This isn't speculation. Astronomers have detected evidence of crystallization in white dwarfs, observing how they cool at rates slightly slower than expected. The crystallization process releases a tiny amount of gravitational energy as atoms settle into their lowest energy configuration. This slows the cooling, adding a few billion extra years to the timeline. But it doesn't stop it. Eventually, every white dwarf will become a completely solid, completely cold diamond. A gem larger than our planet, worth more than all the wealth that ever existed, and completely inaccessible. Just floating in the void. Dark, silent, eternal, or so it seems. The neutron stars are changing too. When they first form in supernova explosions, neutron stars spin incredibly fast, often rotating hundreds of times per second. Their powerful magnetic fields channel radiation into beams that sweep across space like lighthouse beams. We call these pulsars, but nothing spins forever. The rotation gradually slows as the neutron star loses energy to radiation. Over millions of years, a pulsar that once spun 100 times per second slows to 10 times, then once per second, then once per minute. Eventually, it stops pulsing altogether, becoming invisible to our radio telescopes. The magnetic field weakens. The star continues to cool, radiating away its thermal energy into the void. A young neutron star can have a surface temperature of 1,000,000 degrees. But after trillions of years, that drops to thousands of degrees, then hundreds, then near absolute zero. The neutron star is still there, still incredibly dense, still warping space-time around it. But it's cold and dark and silent. Just another corpse in the growing graveyard. Now think about the planets. Not Earth, that's long gone, vaporized when the sun became a red giant. But in other solar systems, some planets survive the death of their stars. Gas giants like Jupiter or Saturn, orbiting far enough out to avoid being consumed when their star swells. These worlds find themselves in a new reality. Eternal night. The star they orbited for billions of years is now a white dwarf, giving off some light but nothing like before. Over time, as the white dwarf cools, even that faint light diminishes. The planet's surface temperature plummets. Any atmosphere freezes and falls as snow. Oceans, if they existed, become solid ice kilometers thick. The planet becomes a frozen ball, its surface to temperature just a few degrees above absolute zero. There's no weather because weather requires energy input. No geological activity because that requires internal heat, which eventually dissipates. No change at all, just a frozen world orbiting a dead star in perfect silence. This state persists for trillions of years. The planet is still there, still orbiting, but it's more like a tomb than a world. Nothing happens on its surface. Nothing will ever happen again. Some planets don't even have that. Rogue planets, ejected from their solar systems during the chaos of stellar death or galactic interactions, drift through intergalactic space with no star at all. These worlds are even colder, even darker, even more alone. Frozen wanderers in the void, traveling forever with no destination. But even these stable orbits won't last forever. There's a subtle effect at work, so slow and weak that we barely notice it today. But given enough time, it becomes significant. When two objects orbit each other, they create ripples in space-time called gravitational waves. These waves carry energy away from the system. Not much energy, the effect is tiny, but over billions and trillions of years it adds up. Two white dwarfs orbiting each other will slowly spiral closer together as gravitational waves drain energy from their orbit. The process takes an incomprehensibly long time. We're talking about 10 to the power of 20 years, maybe longer. That's 100 billion years. But eventually, the orbit decays completely. The two white dwarfs spiral together and merge. What happens next depends on their combined mass. If it's below a certain threshold, they just form a larger white dwarf. If it exceeds that threshold, something dramatic happens. The combined mass is enough to overcome the quantum pressure holding the white dwarf up, and the whole thing collapses into a neutron star. Or, if the mass is even higher, it collapses directly into a black hole. Either way, the merger releases an enormous amount of energy, briefly illuminating the darkness. But there's probably no one around to see it. Planets orbiting white dwarfs experience the same orbital decay. Over 10 to the power of 20 years, they slowly spiral inward. The planet gets closer and closer to its dead star, eventually crossing the Roche limit where tidal forces tear it apart. The debris forms a ring around the white dwarf, then gradually falls onto its surface, adding a tiny amount of new material. The planet is consumed, erased, its atoms scattered. Another structure gone. On even larger scales, galaxies themselves are falling apart. Remember, galaxies are collections of hundreds of billions of stars orbiting around a central supermassive black hole. Or, in this era, hundreds of billions of stellar remnants orbiting around that black hole. These orbits are stable on human timescales, but not on truly cosmic timescales. Over periods of 10 to the power of 19 to 10 to the power of 20 years, gravitational interactions between stellar remnants become significant. When two white dwarfs or neutron stars pass close to each other, they exchange energy. One speeds up, one slows down. The one that speeds up climbs to a higher orbit, farther from the galactic center. The one that slows down falls to a lower orbit, closer to the center. This process repeats over and over. Trillions of close encounters, each one shuffling energy around. Gradually, the galaxy evaporates. About 90% of the stellar remnants gain enough energy to escape the galaxy entirely. They're flung out into intergalactic space, becoming isolated wanderers. These ejected objects are truly alone, separated from the nearest other object by millions or billions of light years. They'll drift through the void for the rest of time, never interacting with anything again. The other 10% of stellar remnants lose energy instead of gaining it. They fall inward, sinking toward the galactic center. Eventually, they fall into the supermassive black hole at the galaxy's core. They cross the event horizon and disappear forever, their mass adding to the black hole's already enormous bulk. The galaxy, which once contained hundreds of billions of stars and stellar remnants, has dissolved. 90% ejected, 10% consumed. What's left behind? Just the supermassive black hole. These monsters sit at the center of what used to be galaxies, now surrounded by absolutely nothing. The Milky Way's central black hole, Sagittarius A star, weighs about 4 million times the mass of the Sun. After consuming 10% of the galaxy's stellar remnants, it's even more massive. Andromeda's central black hole is even larger, billions of solar masses. These objects are now alone in space. No stars orbit them. No gas clouds surround them. They're just massive concentrations of gravity, warping space-time, sitting in the void. Invisible, silent, waiting. Across the universe, billions of these supermassive black holes now exist in isolation, each one marking where a galaxy used to be, each one separated from the others by exponentially expanding space. They're so far apart that they'll never interact, never merge, never even be aware of each other's existence. The universe has become a sparse collection of black holes in an ocean of darkness. For the next immense stretch of time, from about 10 to the power of 20 years to 10 to the power of 40 years, almost nothing happens. The universe enters a period of profound boredom. The scattered stellar remnants floating through intergalactic space continue their journeys to nowhere. The supermassive black holes sit motionless in space. Occasionally, very occasionally, two remnants drift close enough to interact. Maybe once every trillion years, somewhere in the observable universe, two black dwarfs collide. The impact generates heat and light, probably vaporizing both objects. A brief flash in the darkness, quickly fading, then nothing again for another trillion years. Or two neutron stars wandering through space for incomprehensible eons happen by pure chance to pass near each other. Their mutual gravity pulls them together. They spiral inward over millions of years and collide, merging in a kilonova explosion that creates a brief shower of heavy elements, forging gold and platinum that no one will ever use. The explosion fades. Darkness returns. These events are monumentally rare. The universe is so vast and so empty that the average distance between any two objects is larger than the entire observable universe was at the beginning. Most objects will never encounter anything else ever again. They'll drift alone through the void for 10 to the power of 30 years, 10 to the power of 40 years, potentially forever. The temperature of space itself is now incomprehensibly cold. The cosmic microwave background radiation, that faint afterglow of the Big Bang, has been redshifted by expansion for trillions of years. It's no longer microwaves. The wavelength has stretched to meters, then kilometers, then light years. The temperature has dropped to a billionth of a degree above absolute zero. For all practical purposes, the universe is at absolute zero. No energy flows. No heat moves from one place to another. Everything is in thermal equilibrium, or as close to it as quantum mechanics allows. But something else is happening during all this time. Something subtle and profound. Matter itself is starting to become unstable. We think of protons as permanent, eternal, unchanging. The protons in your body are the same protons that existed at the Big Bang. They've never decayed, never transformed into something else. They seem immortal. But theoretical physics suggests they might not be. Grand unified theories, attempts to unite the electromagnetic force, the weak nuclear force, and the strong nuclear force into a single framework, predict that protons can decay. The mechanism is complex, involving quantum tunneling and force unification at extremely high energies. But the prediction is clear. Protons have a half-life. It's staggeringly long, somewhere between 10 to the power of 34 years and 10 to the power of 40 years, depending on which version of the theory you use. We've never observed proton decay. Experiments have watched vast tanks of water containing 10 to the power of 33 protons for decades, waiting for just one to decay. Nothing. But the predicted half-life is so long that this isn't surprising. If the half-life is 10 to the power of 40 years, you would need to watch for 10 to the power of 30 years to see a single decay in that tank. We haven't been watching that long. But given enough time, it will happen. And if it does, it changes everything. Because protons are the building blocks of atomic nuclei. If protons can decay, then atoms can disintegrate, stars can evaporate, planets can dissolve. Everything made of matter has an expiration date. The degenerate era we've been describing, this age of stellar corpses cooling in the void, won't last forever. Eventually, those corpses themselves will decay. Atom by atom, proton by proton, they'll dissolve into radiation. The universe is about to enter an even stranger phase, one where matter itself disappears. Proton decay is unlike anything we normally observe in nature. When a radioactive element decays, the nucleus breaks apart, but the protons remain intact. When matter and antimatter annihilate, they destroy each other, but the energy is conserved. Proton decay is different. The proton itself, the fundamental building block of atomic nuclei, spontaneously transforms into lighter particles. A positron appears. A neutral pion is created, which immediately decays into gamma rays, and the proton is gone. Just gone. This happens at the quantum level through a process so rare and improbable that we've never seen it occur. Grand unified theories predict this should happen with a half-life somewhere between 10 to the power of 34 years and 10 to the power of 40 years. Let me put that in perspective. 10 to the power of 34 years is 10,000 trillion years. That's not a billion times the age of the universe. That's a trillion times the age of the universe. The predicted half-life is so long that calling it astronomical doesn't begin to capture it. But here's the thing about half-lives. They are statistical. Even if the average proton lasts 10 to the power of 40 years, some will decay sooner. If you have enough protons, you'll see decays happening all the time, just at a very slow rate. And a white dwarf contains roughly 10 to the power of 57 protons. That's a lot of protons. Enough that even with this absurdly long half-life, decays are occurring constantly. Imagine a black dwarf floating through space. It's been dark and cold for trillions of years. Surface temperature just a few degrees above absolute zero. Nothing has changed about this object since it finished crystallizing. It's just a sphere of carbon and oxygen crystals drifting through the void. But now we're approaching 10 to the power of 37 years into the universe's history. Something strange begins to happen. Deep in the black dwarf's core, a proton decays. The transformation produces a positron and gamma rays. The gamma rays travel a short distance before being absorbed by surrounding atoms, depositing their energy as heat. This produces a tiny, infinitesimal increase in temperature. By itself, undetectable. But it's not just one proton. With 10 to the power of 57 protons in the black dwarf and a half-life of 10 to the power of 40 years, roughly 10 to the power of 17 protons are decaying every year. That's 100,000 trillion decays per year. Each one releases a small amount of energy. Added together, this energy makes the black dwarf warm. Not hot, but warmer than the surrounding space. The black dwarf begins to glow again, extremely faintly in infrared wavelengths, but it's producing light for the first time in trillions of years. Astronomers have a name for these objects, assuming anyone was around to observe them. They call them the dimmest stars imaginable. Black dwarfs heated not by fusion, but by the quantum decay of their own atomic structure. But this glow won't last forever. As protons decay, the black dwarf is losing mass. Each decay removes one proton from the star's inventory. At first, this is negligible. After a billion years of decay, the star has lost maybe 1/1000% of its mass. But time is long. Very long. By 10 to the power of 38 years, a significant fraction of the star's protons have decayed. By 10 to the power of 39 years, half of them are gone. The black dwarf is literally evaporating. Atoms in the crystal lattice suddenly cease to exist as their protons decay. The structure becomes less dense. The gravitational binding weakens. Eventually, the black dwarf isn't really a solid object anymore. It's a diffuse cloud of electrons, positrons, and gamma radiation where a star used to be. By 10 to the power of 40 years, assuming the proton decay half-life is in this range, the evaporation is essentially complete. The black dwarf has dissolved into radiation and leptons. The particles spread out into space at light speed, becoming more and more diffuse. Within a few thousand years, they are spread across a region larger than galaxies. Within 1,000,000 years, larger than galaxy clusters. The star is gone, not destroyed in any violent sense, just quietly disassembled atom by atom and scattered to infinity. Neutron stars face the same fate, though the process is slightly different. Neutrons, when isolated, are actually unstable. A free neutron will decay in about 15 minutes on average, transforming into a proton, electron, and antineutrino. But neutrons inside a neutron star are stabilized by the immense pressure. They're packed so tightly that quantum mechanics forbids them from decaying. At least that's true in normal circumstances. But proton decay theory suggests that even neutrons can't escape forever. If protons can decay through quantum tunneling and force unification, neutrons can too, just through a slightly different pathway. The math is complex, but the conclusion is the same. Over timescales of 10 to the power of 40 years, even neutron stars will evaporate. The neutrons transform into lighter particles. The star slowly converts its mass into radiation. The density drops. The gravitational binding weakens. Eventually, the neutron star is gone, replaced by an expanding cloud of particles and energy. Every stellar remnant, every white dwarf, every neutron star, every planet, every asteroid, every dust grain, everything made of atoms is dissolving. The universe is engaging in self-cleaning on timescales so vast that trillions of years might as well be seconds. What replaces all this matter? The decay products of proton decay are primarily photons, neutrinos, electrons, and positrons. The photons, gamma rays when first created, rapidly redshift as space continues expanding. They become lower energy X-rays, then ultraviolet, then visible light, then infrared, then radio waves. Eventually, their wavelengths are stretched to astronomical scales, making them effectively undetectable. The neutrinos barely interact with anything. They travel at nearly the speed of light, passing through space without ever colliding with other particles. The electrons and positrons spread out as well. Occasionally, an electron and positron find each other and annihilate, producing more photons. But space is so vast and so empty that most never encounter anything. The universe is transitioning from a state dominated by matter to a state dominated by radiation and leptons. A thin, diffuse soup of particles spread across exponentially expanding space. The density is incomprehensibly low. Maybe 1 particle per volume larger than the observable universe today. The temperature is a tiny fraction of a degree above absolute zero, maintained only by the energy released from the proton decay. But this heat source is temporary. Once all the protons have decayed, once all the neutrons have transformed, the energy production stops. The universe will darken again and grow even colder. By 10 to the power of 40 years, all matter-based objects are gone. The white dwarfs evaporated. The neutron stars dissolved. the planets long since decayed. Even the random debris floating through space, the asteroids and comets and dust grains, all of it has broken down into elementary particles. Nothing solid remains, nothing with structure, nothing with complexity, nothing except black holes. The black holes remain because they don't undergo proton decay. They're not made of protons or atoms. They're pure collapsed space-time. Regions where gravity is so strong that matter has been crushed beyond atomic structure, beyond nuclear structure, beyond anything resembling conventional matter. Black holes are made of space-time curvature itself. And for the last 10 to the power of 40 years, while everything else was decaying and evaporating, the black holes just sat there, unchanged, unaffected, waiting. They are now the only structures left in the universe. Stellar mass black holes, ranging from a few to 100 times the Sun's mass, scattered across space. Supermassive black holes, millions or billions of times the Sun's mass, sitting where galaxy centers used to be. These objects contain virtually all the remaining mass in the universe. Everything else has been converted to radiation and leptons. The black hole era has begun. Black holes have always seemed eternal. Once something falls past the event horizon, it can never escape. The gravity is so strong that even light, the fastest thing that exists, cannot break free. Black holes can only grow, never shrink. They accumulate mass by swallowing anything that comes too close. This process is one way. Irreversible. Or so physicists thought until 1974, when Stephen Hawking made one of the most profound discoveries in theoretical physics. He was trying to understand what happens when you combine quantum mechanics with general relativity near a black hole's event horizon. The math is complex, involving virtual particle pairs and vacuum fluctuations, but the conclusion was shocking. Black holes aren't perfectly black. They emit radiation. Hawking radiation, as it's now called. The mechanism works like this. In quantum mechanics, empty space isn't truly empty. It's filled with virtual particle pairs that pop into existence and annihilate each other in tiny fractions of a second. An electron and positron appear, exist for a moment, then destroy each other. This happens everywhere, all the time, but the particles exist for such a short time that we can't detect them directly. Near a black hole's event horizon, something different can happen. A virtual particle pair appears right at the edge. One particle falls into the black hole. The other escapes into space. The escaping particle is now real, not virtual. It becomes a permanent addition to the universe. But energy must be conserved. Where did the energy to create this real particle come from? It came from the black hole's mass. The black hole loses a tiny amount of mass energy to produce the escaping particle. This is Hawking radiation. The black hole is evaporating. The rate of evaporation depends on the black hole's mass. Specifically, it's inversely proportional to the square of the mass. A small black hole evaporates quickly. A large black hole evaporates slowly. Very, very slowly. Let's start with stellar mass black holes, the remnants of massive stars. Consider a black hole with 10 times the Sun's mass, which is typical for these objects. Hawking's equations tell us this black hole will completely evaporate in about 10 to the power of 67 years. Let me emphasize how long that is. We've already talked about 10 to the power of 40 years, which seemed incomprehensible. This is 10 to the power of 27 times longer. If you wrote out 10 to the power of 67 as a regular number, it would be a 1 followed by 67 zeros. 100 million trillion 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 years. During most of this time, the black hole barely changes. The Hawking radiation it emits is incredibly faint. The temperature of the radiation is inversely proportional to mass, so a 10 solar mass black hole has a temperature of about a millionth of a degree above absolute zero. It's radiating energy, but so slowly that it would take billions of years to lose the mass equivalent of a single proton. The black hole just sits in space, invisible, nearly unchanging, for eon after eon. Space around it is utterly empty. All the matter has already decayed. There's nothing for the black hole to consume. It can only radiate, slowly, inexorably, forever losing mass. But here's where it gets interesting. As the black hole loses mass, the evaporation accelerates. Remember, the radiation rate is inversely proportional to mass squared. Cut the mass in half and the radiation rate quadruples. This creates a runaway process. The black hole radiates and loses mass. Losing mass makes it radiate faster. Radiating faster makes it lose mass more quickly. The process accelerates. For the vast majority of the black hole's lifetime, this acceleration is negligible. The first 10 to the power of 66 years see very slow, steady evaporation. But in the final 10 to the power of 50 years, things start to change noticeably. The black hole has lost enough mass that its temperature has risen to thousands of degrees. It's now glowing in infrared and visible light. Still incredibly faint, but detectable if anyone were around to look. The evaporation continues to accelerate. The final million years are dramatic. The black hole's temperature rises to billions of degrees. It's now a brilliant source of gamma rays and high-energy particles. The event horizon is shrinking rapidly, contracting from kilometers across to meters to centimeters. In the final year, the black hole weighs about as much as a mountain but is smaller than an atom. Its temperature is trillions of degrees. The final second is an explosion. The black hole's mass drops to nearly zero. The temperature spikes to essentially infinite. Energy pours out in all directions. Gamma rays, neutrinos, particle-antiparticle pairs, everything allowed by physics. And then, in an instant, the black hole is gone. Completely. The event horizon vanishes. The space-time curvature relaxes back to flatness. Where there was once a black hole containing the mass of 10 suns, there's now just empty space and a rapidly expanding sphere of radiation and particles. What about the supermassive black holes? These monsters dwarf their stellar mass cousins. The supermassive black hole at the center of our Milky Way weighs about 4 million solar masses. Some supermassive black holes weigh billions of solar masses. The evaporation time scales with mass cubed. Double the mass and the evaporation takes 8 times longer. A supermassive black hole with a billion solar masses will take approximately 10 to the power of 100 years to completely evaporate. This is the big number, the final number, the longest time scale that matters in the universe. 10 to the power of 100 years, a guogal years. This number is so large that comparisons fail. The number of atoms in the observable universe is only about 10 to the power of 80. If every atom was a year, you still wouldn't reach 10 to the power of 100. If every atom was a universe, and every atom in each of those universes was a year, you'd start to approach it. The number breaks human comprehension. It's effectively infinite for any practical purpose. But it's not actually infinite. It's a finite number. The supermassive black holes will evaporate, all of them, every single one, given enough time. During most of the black hole era, nothing happens. The universe between 10 to the power of 40 years and 10 to the power of 67 years is monumentally boring. Stellar mass black holes sitting in space, emitting Hawking radiation too faint to detect, surrounded by nothing. Supermassive black holes, even less active, even more isolated. The occasional stellar mass black hole completes its evaporation, producing a brief flash of energy. But these events are rare. Space is so vast that the average distance between black holes is larger than the observable universe was at the beginning. Most black holes will never be aware another black hole exists. They're alone in the truest sense of the word. No matter nearby. No light reaching them from any source. Just warped space-time and their own faint Hawking radiation. From 10 to the power of 67 years onward, stellar mass black holes begin evaporating in earnest. Not all at once, but in sequence as each one reaches the end of its individual timeline. Every few trillion years, somewhere in the universe, a stellar mass black hole completes its final evaporation. There's a flash of gamma rays, a burst of particles, then nothing. Darkness returns. This continues for incomprehensible time. Every 10 to the power of 20 years, another flash somewhere. Then silence for 10 to the power of 20 more years. The universe is experiencing events, technically, but they're so spread out in space and time that calling them events seems generous. They're quantum hiccups in an otherwise static eternity. By 10 to the power of 90 years, all the stellar mass black holes are gone. Every single one has evaporated. Only the supermassive black holes remain. These giants are barely beginning their evaporation. They've been sitting in space for 10 to the power of 90 years, essentially unchanged. Their Hawking radiation is so faint, their temperature so low that they might as well be part of the background. But they're evaporating. Slowly, atom by atom, or whatever the black hole equivalent of an atom is. They're losing mass. Each supermassive black hole is now completely alone. The expansion of space has carried other black holes so far away that they're beyond any possible horizon. Light from other black holes, if they were emitting any, could never reach. The universe has become a collection of causally disconnected regions, each containing a single supermassive black hole, each evolving independently. From the perspective of one of these black holes, it's the only thing that exists, the only structure, the only mass, the only source of gravity in the entire universe, at least in its observable universe, and it's dying. Slowly, but dying. The final approach to 10 to the power of 100 years. The largest supermassive black holes are now in their final stages of evaporation. A black hole that once weighed 1 billion times the Sun's mass has been reduced to 1 million solar masses. Its temperature has risen from 1/1000th of a degree to 1/100000th. Still cold by any normal standard, but rising. The evaporation continues to accelerate. At 10 to the power of 99 years, the black hole weighs only 10,000 solar masses. Temperature measured in millidegrees, definitely warmer now. The final million years arrive. The black hole has shrunk to 100 solar masses, then 10, then 1. The temperature is now thousands of degrees, then millions. The black hole is radiating furiously, pouring energy into the void. It shrinks to the mass of a planet, then a mountain, then a boulder. The temperature reaches billions of degrees, then trillions. The final year, the final day, the final second. The black hole has contracted to smaller than an atom. Its temperature is beyond anything we can measure. Quantum gravity effects dominate. Space-time itself is fluctuating wildly. And then, approximately 10 to the power of 100 years after the Big Bang, The last supermassive black hole in the universe evaporates in a final burst of radiation. The explosion releases all the remaining mass energy in one violent instant. Particles and radiation expanding outward at light speed, and then it's over. The black hole is gone. The universe now contains no structures, no objects, no complexity, just a thin soup of radiation and elementary particles spread across infinite space. The black hole era has ended. What comes next is worse than death. Its eternal, unchanging existence. The heat death of the universe. But wait, what if proton decay doesn't happen? Or what if it happens much more slowly than predicted? Grand unified theories aren't proven. We've never observed a proton decay despite decades of experiments. The predicted half-life of 10 to the power of 34 to 10 to the power of 40 years is theoretical. What if the real number is 10 to the power of 100 years? Or 10 to the power of 1,000 years? Or what if protons are actually stable and never decay at all? If that's true, then all those white dwarfs and neutron stars we discussed won't evaporate. They'll persist as solid objects for much, much longer. But they won't remain unchanged. Something else will happen to them. Something even stranger than proton decay. They'll transform into iron. Not through any conventional process like stellar fusion, through quantum tunneling. Let me explain. At temperatures near absolute zero, quantum mechanics dominates over classical physics. Particles can do things that seem impossible, like tunneling through energy barriers they shouldn't be able to cross. In a white dwarf made of carbon and oxygen, the nuclei are locked in a crystal lattice. They're in a specific configuration. But that configuration isn't the lowest possible energy state. The lowest energy configuration for nuclear matter is iron 56. Iron is the most stable nucleus. It has the highest binding energy per nucleon. If you could convert all the carbon and oxygen in a white dwarf into iron, you'd release energy and reach a lower energy state. But this conversion requires fusion reactions that need high temperatures and pressures. The white dwarf is cold. No fusion is happening. Except quantum tunneling allows particles to bypass energy barriers. Given enough time, incomprehensible amounts of time, the carbon and oxygen nuclei can tunnel into iron nuclei. The probability of this happening to any single nucleus in a reasonable time frame is essentially zero. But there are 10 to the power of 57 nuclei in a white dwarf. And we have all the time in the universe, literally. The calculations suggest this transformation takes about 10 to the power of 1,500 years. Let me be clear about what that number means. It's not 10 to the power of 15, which would be 1,000,000 billion. It's not 10 to the power of 150, which would already be incomprehensible. It's 10 to the power of 1,500. A 1 followed by 1,500 zeros. If you tried to write this number out, with each zero taking up 1 millimeter of space, the number would stretch for 1.5 meters. And that's just to write the number, not to count it or comprehend it. This timescale is so vast that 10 to the power of 100 years, the time it takes supermassive black holes to evaporate, is nothing in comparison. A trillion, 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 trillion times longer. During this incomprehensible stretch of time, quantum tunneling events slowly convert the white dwarf's composition. A carbon nucleus here tunnels into iron. An oxygen nucleus there does the same. Each conversion releases a tiny amount of energy. Not much, but over 10 to the power of 1,500 years, it adds up. The white dwarf, which has been cold and dark for longer than we can express, begins to warm slightly from these quantum tunneling fusion reactions. Eventually, after 10 to the power of 1500 years have passed, the entire white dwarf has transformed. What was once carbon and oxygen is now pure iron-56. The star has become an iron star, a cold, crystalline sphere of the most stable element. Dark, dense, seemingly eternal. But even iron stars aren't safe forever. The same quantum tunneling that created them will eventually destroy them. Iron-56 might be the most stable nucleus, but it's not the most stable form of matter. That distinction belongs to black holes. Given enough time, quantum tunneling can cause the entire iron star to collapse. Not through gravitational collapse in the classical sense, through quantum tunneling directly into a black hole state. The probability of this happening is absurdly low. We're talking about 10 to the power of 10 to the power of 26 years. That's not a typo. It's 10 to the power of a number that's itself 10 to the power of 26. You can't write this number in any meaningful way. If every digit was an atom, and you used all the atoms in the observable universe, you couldn't write this number. It exceeds any sense of time. But in principle, given infinite time, the iron star will quantum tunnel into a black hole. The entire stellar mass, all at once, will spontaneously collapse. One moment there's an iron star. The next moment there's a black hole of equivalent mass. And then that black hole will evaporate through Hawking radiation over 10 to the power of 100 years or so. The iron star's attempt at immortality fails. Everything ends. Let's consider what else might persist in the far future. After all the matter has decayed or collapsed, the universe will contain mostly photons, neutrinos, electrons, and positrons. The photons will continue traveling forever. They're massless, stable particles. They never decay, but they do change. As space expands, the wavelength of light stretches. This is cosmological redshift. A photon that starts as a high-energy gamma ray will redshift to become an X-ray, then ultraviolet, then visible light, then infrared, then a microwave, then a radio wave. The wavelength keeps stretching. After 10 to the power of 100 years, photons that started with wavelengths measured in nanometers will have wavelengths measured in light years. After 10 to the power of 200 years, wavelengths larger than galaxy clusters. Eventually, the wavelength becomes larger than the observable universe itself. At that point, does the photon even exist in any meaningful sense? It's spread across a region so vast that no observer could ever detect it. The photon is technically still there, still traveling, still carrying its tiny quantum of energy. But for all practical purposes, it's become nothing. The same applies to neutrinos. These ghostly particles barely interact with matter. They can pass through a light year of solid lead without being absorbed. In the far future, with no matter left to interact with, neutrinos will travel forever. Each one alone, separated from others by distances larger than galaxies. They'll never collide, never interact, never do anything. Just traveling through empty space at nearly the speed of light. Forever. Electrons and positrons are more interesting. These are antiparticles of each other. When an electron and positron meet, they annihilate, converting their mass into energy in the form of photons. In the dense early universe, this happened constantly. But in the far future, space is so vast and empty that an electron might travel for 10 to the power of 50 years without encountering a positron. When they do rarely meet, something curious can happen before annihilation. The electron and positron can form an atom called positronium. In normal conditions, Positronium is incredibly unstable. It decays in about 1/10 of a microsecond. But that's because the electron and positron are close together, orbiting at high speed. In the cold, empty far future, electrons and positrons can form positronium atoms in highly excited states. Huge atoms where the electron and positron orbit each other at enormous distances. The orbital radius could be larger than planets, larger than stars. In principle, larger than entire galaxies. These ghost atoms would be the least dense objects imaginable. Two particles orbiting each other with light years of empty space between them. The orbital period would be millions of years. Eventually, the positronium atom will decay. The electron and positron will spiral together and annihilate. But for a brief time, measured in millions or billions of years, these cosmic atoms exist, the largest atoms possible. Quantum mechanics operating on galactic scales. Now, let me introduce the most disturbing concept in far future cosmology. Boltzmann brains. The idea comes from statistical mechanics and the nature of entropy. In an infinite universe with infinite time, even the most improbable events will eventually happen. Quantum fluctuations, random variations in the vacuum energy, happen constantly at the microscopic scale. These fluctuations average out to zero, so we don't notice them. But given infinite time, eventually a fluctuation will occur that's much larger than average. A fluctuation that creates a small amount of organized matter. The probability of creating a single proton from random fluctuations is incredibly low, but it's not zero. Given 10 to the power of 100 years, it might happen. Given 10 to the power of 1,000 years, it will probably happen. The probability of creating an entire atom is much lower. Creating a molecule, lower still. But in infinite time, even these will occur. Now, here's where it gets weird. The probability of a random quantum fluctuation creating an entire functioning human brain is absurdly, unimaginably low. But it's higher than the probability of creating an entire universe. A brain is smaller and simpler than a universe. So, in infinite time, you're more likely to see a brain spontaneously appear from quantum fluctuations than you are to see a new Big Bang. This spontaneously created brain, called a Boltzmann brain, would exist for just a moment. It would have memories of a life it never lived. It would think one thought, maybe experience one moment of consciousness, then it would dissipate back into the quantum vacuum. These phantom consciousnesses might be the only observers in the far future universe, appearing randomly, thinking briefly, vanishing, forever. But let's get back to something more concrete. Could an advanced civilization survive into the far future? Could intelligence persist when all the stars are dead? It sounds impossible, but some physicists have explored the idea. The key would be finding an energy source. In the far future, after all stars have died and all matter has decayed, the only energy sources are Hawking radiation from black holes. A sufficiently advanced civilization could, in theory, position itself near a black hole and harvest the radiation. The amount of energy would be tiny. A stellar mass black hole emits only about 10 to the power of negative 28 watts. That's watts. Barely enough to power a single atom. But with perfect efficiency and very slow thinking, maybe it's enough. The civilization would need to slow down their subjective experience of time. Instead of thinking at human speeds, they'd think one thought per billion years. To them, time would feel normal, but to an outside observer, they'd appear frozen, nearly static, barely alive. This civilization would cluster around black holes, using them as power sources. As one black hole neared complete evaporation, they'd migrate to another. A cosmic game of musical chairs. Each migration would take billions of years of travel time, but they have all the time in the universe. They'd hop from black hole to black hole, extending their existence. But the music has to stop eventually. Black holes are evaporating. Each one that dies is one fewer energy source. The civilization would need to be increasingly strategic about which black holes to cluster around. They'd migrate to the largest ones, the supermassive black holes that will last longest. Billions of years would pass in their slow, subjective time. They'd watch stellar mass black holes evaporate one by one. Each evaporation would be like watching a star go supernova. A brief flash of energy, then darkness. The civilization would move to ever larger black holes, from millions of solar masses to billions, conserving energy, thinking slower and slower. Eventually, only one black hole would remain, the very last one. The largest supermassive black hole in their observable region of space. Every surviving consciousness from across vast reaches of space would need to converge here. The last gathering place, the final campfire. They'd cluster around this black hole, knowing there's nowhere else to go. They'd watch it evaporate. Year by year, the black hole would shrink. Its temperature would rise. The Hawking radiation would intensify. This is good news at first. More energy means they can think faster. The civilization might experience a brief renaissance. More power available than they've had in trillions of years. But it's temporary. The increasing radiation also means the black hole is dying faster. They'd be forced to watch as their final energy source accelerates toward oblivion. Imagine being part of this civilization in those final subjective years. You'd know with absolute certainty that no escape exists. You've checked. You've sent probes across billions of light years. There are no other black holes within reach. This is the last one. In a few subjective years, by your slow time reckoning, it will evaporate. And then you die. Not just you individually. Everyone. Everything. The entire history of your civilization, which survived through the death of all stars and the decay of all matter, ends here. You'd watch the black hole shrink. Calculations would tell you exactly how long remains. 1 year, 1 month, 1 day. The black hole would be glowing now, bright and hot. More energy than you've ever had access to. But it's the energy of death. The final burn before the darkness. The last hour, the last minute. The black hole is smaller than an atom now, radiating at unimaginable intensity. You'd see it happen. The final second, the explosion, a burst of particles and radiation. And then, nothing. No energy source. No way to power computation. No way to think. Your consciousness would cease not because you died in any conventional sense, but because the substrate supporting your existence has vanished. The lights go out, forever. After the last black hole evaporates, the universe settles into its final state. Heat death. Maximum entropy. This isn't a single moment, but a condition that persists forever. The universe still exists. Space and time continue, but nothing happens. Let me explain what maximum entropy means. Entropy is a measure of disorder, or more precisely, a measure of how spread out energy is. A hot star radiating into cold space is a low entropy state. Energy is concentrated in the star. It can flow from hot to cold, doing work in the process. The second law of thermodynamics says entropy always increases. Energy spreads out. temperatures, equalize. Eventually, you reach a state where energy is spread perfectly uniformly. No hot regions, no cold regions, just one universal temperature everywhere. This is maximum entropy, and when you reach it, nothing interesting can happen anymore. All processes require energy to flow from high concentration to low concentration. When there's no difference in concentration, no processes can occur. The universe reaches thermodynamic equilibrium. Not death in the sense of something actively ending, but stasis. Perfect, unchanging, eternal stasis. The temperature of this heat-death universe is not exactly absolute zero. It's slightly above it. For all practical purposes, it's absolute zero. At this temperature, no chemistry can occur. No biological processes, no computation, no consciousness. Even if you had a perfect computer with perfect power efficiency, you couldn't run it because there's no energy gradient to power it. The universe contains photons with wavelengths larger than galaxies, neutrinos that will never interact, a few electrons and positrons separated by incomprehensible distances. That's it. No structures, no complexity, no change. Time continues to pass. Space continues to expand. But nothing happens. Not in a billion years. Not in 10 to the power of 100 years. Not ever. Events require energy differences. When everything is at the same temperature, events become impossible. The universe has reached a state where the concept of events becomes meaningless. You could wait 10 to the power of 1,000 years, and nothing would be different. Wait 10 to the power of 1,000 years, and it's still the same. The universe persists, but it's functionally over. This is worse than death. Death implies an ending. This is existence without meaning, without change, without possibility. Forever. We have been discussing the death of normal matter, but we've been ignoring something crucial. Normal matter, the protons and neutrons and electrons that make up everything we can see and touch, only accounts for about 5% of the universe. Another 27% is dark matter. We don't know what dark matter is. We can't see it. We can't detect it directly. We only know it exists because of its gravitational effects. Galaxies rotate faster than they should based on visible matter alone. Galaxy clusters are held together by more mass than we can account for. Gravitational lensing reveals invisible mass bending light. All the evidence points to enormous quantities of matter that doesn't interact with light. Dark matter. The leading candidates are WIMPs, weakly interacting massive particles, or axions, or sterile neutrinos. But we don't know. We have built detectors deep underground, shielded from cosmic rays, waiting for a dark matter particle to collide with normal matter. Nothing yet. Decades of searching, and we've found no direct evidence. But here's the critical question for the far future. Does dark matter decay? If dark matter is made of particles, and all particles we know of are either stable or unstable, then dark matter particles must be one or the other. If they're stable, they last forever. If they're unstable, they have a half-life. And if that half-life is longer than the proton's half-life, then dark matter will outlast normal matter. It could survive for 10 to the power of 50 years, or 10 to the power of 100 years, or even longer. We don't know. We can't know until we figure out what dark matter actually is. But imagine if dark matter persists after everything else has decayed. The universe at 10 to the power of 50 years would contain invisible particles we can't detect spread across exponentially expanding space. They'd be the last remnants of matter in any conventional sense. Eventually, even they would decay or perhaps interact with each other in ways we don't understand. Dark matter might form structures we've never imagined, or it might just spread out uniformly. We're speculating in complete ignorance here. Then there's dark energy. This is even more mysterious than dark matter. Dark energy makes up approximately 68% of everything in the universe. It's responsible for accelerating cosmic expansion. But we have no idea what it is. The simplest explanation is that it's a cosmological constant, a fundamental property of space itself. Every cubic meter of space contains a fixed amount of dark energy. As space expands, more cubic meters come into existence, so the total amount of dark energy increases. This pushes space apart even faster. The expansion accelerates. Forever. This is the current best model, and it leads to the heat death scenario we've been describing. But there are alternatives. Some theories propose that dark energy isn't constant. It might strengthen over time. This is called phantom energy. If dark energy grows stronger, it doesn't just accelerate expansion. It eventually overwhelms every other force in the universe. First, it overcomes the gravity holding galaxy clusters together. The clusters disperse. Then it overcomes the gravity of individual galaxies. Galaxies tear apart, stars flung in all directions. Then it overcomes the gravity holding solar systems together. Planets are ripped away from their suns. It gets worse. The phantom energy continues strengthening. Eventually, it overcomes electromagnetic forces, the bonds that hold molecules together. Every solid object in the universe disintegrates into atoms. But the phantom energy isn't done. It strengthens further until it overcomes the strong nuclear force. Atomic nuclei split apart. Protons and neutrons separated. Finally, in the last fraction of a second before the end, the phantom energy becomes infinite. It tears apart space-time itself. This is called the Big Rip. If the Big Rip is real, the timeline is much shorter than heat death. Conservative estimates put it 200 billion years in the future. More aggressive calculations suggest as soon as 22 billion years. That's barely longer than the current age of the universe. We could be living in a cosmos that has less than 20 billion years remaining before it tears itself apart. Here's what the Big Rip would look like. Right now, 13.8 billion years after the Big Bang, dark energy is gently pushing galaxies apart. We barely notice it on scales smaller than galaxy clusters. But if dark energy is strengthening, we'd start to notice changes in a few billion years. Distant galaxies would accelerate away faster than they should. Then, about 100 million years before the Big Rip, galaxy clusters would begin to unbind. The galaxies in the Virgo cluster, currently held together by gravity, would fly apart. About 60 million years before the end, the Milky Way and Andromeda, currently on a collision course, would instead be pushed apart. Merger canceled. The pull of dark energy would exceed their mutual gravitational attraction. 3 months before the Big Rip, individual galaxies would dissolve. Stars ejected from their home galaxies at increasing speeds. 30 minutes before the end, solar systems would unbind. Earth would be flung away from the sun. We'd be alone in space, hurtling through the dark. In the final seconds, molecules would tear apart, then atoms, then atomic nuclei. In the final instant, space-time itself would shred. The metric defining distances would become infinite. The universe would end not in cold silence but in violent dissolution. But current evidence suggests this won't happen. Measurements of dark energy over cosmic history show it's remained constant. Not growing, not shrinking, just a steady cosmological constant. This means no Big Rip. We get heat death instead. The universe expands forever, temperatures drop toward absolute zero, everything spreads apart until maximum entropy is reached. Most cosmologists consider this the most likely fate. Heat death over Big Rip. Slow fade over violent end. But there's one more possibility we need to consider. Something even more final than the Big Rip. Vacuum decay. The idea is that our universe might be in a metastable state. Think of a ball sitting in a shallow valley on the side of a hill. It's stable for now. It's not rolling, but it's not in the lowest possible energy state. The lowest point is at the bottom of the hill. The ball could, in principle, quantum tunnel through the valley wall and roll down to the true minimum. Our universe might be that ball. The vacuum, empty space itself, might not be in its lowest energy state. We might be in what's called a false vacuum, a state that seems stable but is actually just temporarily stable. Eventually, through quantum tunneling, a small region of space could decay to the true vacuum state. Lower energy, different physics. This would create a bubble of new physics expanding at the speed of light. Inside the bubble, the fundamental constants would be different. The masses of particles would change. The strengths of forces would change. Atoms as we know them couldn't exist. The chemistry and physics we depend on would simply stop working. The terrifying part is that vacuum decay could happen anywhere, anytime, with no warning. You wouldn't see it coming. It propagates at light speed. By the time you saw the bubble approaching, it would already be here. Everything you are would be disassembled at the most fundamental level. Not destroyed, but transformed into something governed by alien physics. The matter making up your body would cease to follow the rules that allow you to exist. This wouldn't just kill life or destroy planets. It would erase the possibility of the universe ever producing complexity again. The new vacuum state might not allow for atomic nuclei to form, or electrons to orbit, or any kind of structure. Reality itself would be rewritten, and there's no way to prevent it or survive it or escape it. If vacuum decay is possible and we're in a false vacuum, then our universe has an expiration date we can't calculate. It could happen in the next second. It could happen in 10 to the power of 1,000 years. The probability is completely unknown. Some physicists find this possibility deeply disturbing. Others argue that if vacuum decay were likely, it probably would have happened already given the universe's age. The fact that we're still here suggests either the vacuum is truly stable or the decay probability is incredibly low. But we don't know. We can't know. The math of quantum field theory suggests our vacuum might be metastable, but calculating the tunneling probability is beyond our current capabilities. But let's set aside these exotic possibilities. Let's ignore dark matter decay rates we can't measure, phantom energy we have no evidence for, and vacuum decay we can't predict. Let's focus on what we know with certainty. What is the last object, the last structure, the last thing with any complexity that will exist before the universe becomes completely uniform? The answer is definitive, unambiguous. The largest supermassive black holes. These are the objects that will survive longest. Not dark matter, which might decay. Not smaller black holes, which evaporate sooner. Not any exotic remnant or speculative structure. The biggest black holes are the final survivors. Period. This is guaranteed by physics. Hawking radiation depends on mass. Larger black holes evaporate slower. The relationship is precise. A black hole's evaporation time is proportional to its mass cubed. Double the mass, 8 times longer evaporation. A billion solar mass black hole lasts a billion cubed times longer than a 1 solar mass black hole. The numbers are locked in by equations we trust completely. So, what's the largest black hole we know? The current record holder is Ton 618, a supermassive black hole at the center of a quasar 10.4 billion light-years away. This monster weighs approximately 66 billion times the Sun's mass. That's not million, that's billion. 66,000 on solar masses. The event horizon of this black hole has a diameter of about 300 astronomical units. That's 40 times larger than Neptune's orbit around our Sun. You could fit hundreds of solar systems inside its event horizon. When will Ton 618 evaporate completely? Plug the mass into Hawking's equations and you get approximately 2.1 times 10 to the power of 100 years. Even writing it out doesn't convey the scale. This is a Google years multiplied by 2. This is the longest definite timeline in physics, longer than proton decay timescales, which are uncertain, longer than iron star formation timescales, which are speculative, longer than any other process we can calculate. Ton 618 will be the last significant object in the universe. Now, there might be even larger black holes we haven't discovered yet, possibly in the centers of massive elliptical galaxies or in regions of space we can't observe well. But even if there's a black hole twice as massive as Ton 618, it only lasts about 8 times longer. We're still talking about 10 to the power of 100 years, give or take a factor of 10. The precise number doesn't matter. The point is clear. Supermassive black holes are the final survivors, and the largest ones will be the very last things to exist before the universe reaches maximum entropy. Imagine being that black hole. Not just any black hole, the last one. For eons beyond counting, you've been alone. All other black holes evaporated millions or billions or trillions of years ago. You watched them go, one by one, brief flashes in the darkness as they completed their evaporation. Now you're the only structure left. No galaxies anywhere in your observable region. No stars, no planets, no other black holes. Just you and exponentially expanding empty space. The expansion of space has been accelerating for 10 to the power of 100 years. Any region that was initially far from you is now so distant that light from it could never reach you. You're causally disconnected from most of the universe. For all practical purposes, you are the universe. The only thing in it, the only mass, the only gravity, the only curve in space-time. Everything else is just photons with wavelengths larger than galaxy clusters and a few scattered leptons that will never interact. You're evaporating, of course. You've been evaporating since you formed. But the rate was so slow for so long that you barely noticed. For the first 10 to the power of 99 years, your mass decreased by less than 1%. But now, in your final 10 to the power of 98 years, things are changing noticeably. You've lost a significant fraction of your mass. Your temperature, which was a trillionth of a degree above absolute zero, has risen to a billionth of a degree. Still cold beyond human comprehension, but warming. The process accelerates. At 10 to the power of 99.5 years into your evaporation, you weigh only 10 billion solar masses instead of 66 billion. Your temperature has risen to a millionth of a degree. The Hawking radiation you emit, always present but always negligible, is now detectable. If anyone were around with instruments, they'd notice you glowing faintly in the deepest infrared. The final million years arrive. You now weigh only 100 million solar masses. Temperature measured in millidegrees. The radiation is intensifying. You're shrinking visibly now, at least on cosmological timescales. The event horizon contracts inward. Year by year, kilometer by kilometer, you're getting smaller. The final 10,000 years. Your mass drops to 1 million solar masses. Temperature rising to degrees above absolute zero. Actual degrees, not fractions. You're radiating in infrared, then visible light. If anyone could see you, you'd appear as a dim red glow. The final year. You weigh only 10,000 solar masses. Temperature measured in thousands of degrees. You're glowing bright red now, then orange, then white. The radiation is pouring off you. You're shrinking rapidly, meters per second, then kilometers per second. The final day. You weigh what a large star weighs. Temperature millions of degrees. You're radiating gamma rays and particles at an incredible rate. The event horizon, once larger than solar systems, is now smaller than planets, still contracting. The final hour. You weigh what a mountain weighs. Temperature billions of degrees. The event horizon is smaller than a building, then smaller than a person, then smaller than an atom. The final second arrives. You weigh approximately 1 billion kilograms, the mass of a large building, but you're compressed into a region smaller than a proton. Your temperature is 10 to the power of 32 Kelvin. That's hotter than anything that's ever existed. Hotter than the Big Bang at its first instant. The quantum gravity regime. Space-time around you is fluctuating violently. The distinction between space and time breaks down. Quantum mechanics and general relativity are screaming at each other. The theories we use to describe reality are both operating at full strength, and they fundamentally disagree. We don't actually know what happens next. We don't have a theory of quantum gravity. String theory, loop quantum gravity, other approaches all make different predictions. But they all agree on one thing. The black hole ends completely. In the final microsecond, your mass drops to zero. The event horizon vanishes. All your remaining mass energy converts to radiation. A flash of gamma rays and high-energy particles explodes outward at light speed. The intensity is beyond description. For that 1 microsecond, you're the brightest thing in the universe. Actually, you're the only thing in the universe producing any significant energy. Then it's over. The flash expands outward, red shifting as it travels. Within a few thousand years, it's spread across a region larger than the observable universe once was. The particles and photons join the thin background of radiation that fills space. You're gone. Completely. Permanently. Where there was once a black hole containing 66 billion times the sun's mass. Where there was once the last structure in the universe, the last complexity, the last source of gravity, there's now just empty space and a rapidly dispersing sphere of radiation. The universe has reached its final state. We've traveled from today to the end of everything. Let me summarize what we've witnessed because the journey has been so long and so strange that it's easy to lose perspective. Stage 1 is the death of stars. This spans from now until about 100 trillion years in the future. During this era, the universe transitions from a vibrant place filled with shining stars to a dark graveyard of stellar corpses. The last red dwarf fades. Star formation stops completely. Galaxies become invisible. This takes 100 trillion years, which sounds like forever, but it's just the prologue. Stage 2 is the degenerate era, from 100 trillion years to 10 to the power of 40 years. The universe is now dominated by white dwarfs, neutron stars, and black holes. These objects cool slowly. Orbits decay. Galaxies evaporate. And if proton decay occurs as predicted, all matter-based objects dissolve atom by atom into radiation. This era lasts incomprehensibly longer than Stage 1. If Stage 1 was a single second, Stage 2 would be trillions of years. Stage 3 is the black hole era, from 10 to the power of 40 years to 10 to the power of 100 years. All normal matter is gone. Only black holes remain. They slowly evaporate through Hawking radiation. Stellar mass black holes go first. Supermassive black holes last longest. This era dwarfs everything that came before. If Stage 2 was a single second, Stage 3 would last billions of times the current age of the universe. And Stage 4 is heat death, beginning at 10 to the power of 100 years and lasting forever. The last black hole evaporates. Maximum entropy is reached. The universe becomes completely uniform. Nothing interesting can ever happen again. Not in a billion years. Not in 10 to the power of 1,000 years. Not ever. This state persists eternally. Why is this inevitable? Why can't the universe avoid this fate? The answer lies in one of the most fundamental laws of physics. The second law of thermodynamics. Entropy always increases in a closed system. Always, without exception. Entropy measures how spread out energy is. A hot star radiating into cold space is low entropy. Energy is concentrated. It can flow, do work, make things happen. But energy naturally spreads from hot to cold. The star radiates. Space absorbs the heat. Eventually, temperatures equalize. Energy is now uniformly spread. This is high entropy. You can't reverse this process without adding energy from outside. But the universe is a closed system. There is no outside, no external energy source. The universe can only increase its entropy or maintain it. It can never decrease. This means the universe is moving inexorably toward maximum entropy, toward heat death. Every star that shines increases entropy. Every chemical, reaction, every thought in your brain, every process that occurs anywhere in the universe increases the total entropy. We're all contributing to the heat death, not through carelessness or negligence, but through the fundamental nature of physical law. You cannot stop entropy increase any more than you can make water flow uphill without pumping it. The second law isn't a suggestion. It's not something advanced technology can circumvent. It's woven into the structure of reality itself. Heat death is guaranteed. But wait, some say, what about cyclic models of the universe? What if the universe expands and then contracts? The Big Bang, followed by expansion, followed by contraction, followed by the Big Crunch. Then a new Big Bang, and the cycle repeats. Doesn't that avoid heat death? In the past, this seemed possible. If the universe contained enough matter, gravity might eventually overcome expansion and pull everything back together. The universe would collapse. All matter and energy would compress back into a singularity. Maybe that could trigger a new Big Bang. A phoenix universe, dying and being reborn. Roger Penrose has even proposed a sophisticated version of this called conformal cyclic cosmology, where the heat death of one universe becomes the low entropy initial state of the next. Beautiful idea. Philosophically satisfying. But it doesn't match observations. The discovery of dark energy changed everything. The universe isn't just expanding, it's accelerating. The expansion rate is increasing. This acceleration is driven by dark energy, which doesn't dilute as space expands. More space means more dark energy means faster expansion. There's no mechanism for this to reverse. No big crunch will occur. The universe will expand forever. Some cyclic models try to work around this by proposing that dark energy might change over time, or that quantum effects could nucleate a new Big Bang from the heat-death state. But these ideas are speculative. They require new physics we have no evidence for. Based on what we know, cyclic models fail. We get one universe, one expansion, one heat-death, no rebirth. There's another profound mystery lurking in all this: the black hole information paradox. When you throw a book into a fire, the information contained in the book isn't destroyed. The information is scrambled and dispersed, but in principle, if you could track every atom and every photon, you could reconstruct what was written. Quantum mechanics insists that information is never truly destroyed. It's a fundamental principle. But black holes seem to violate this. When something falls into a black hole, it disappears past the event horizon. All information about what fell in seems to be lost. The black hole has only three properties that can be measured from outside: mass, charge, and spin. Everything else is hidden. Then the black hole evaporates through Hawking radiation. The radiation appears to be completely random, carrying no information about what fell in. So, where did the information go? Was it destroyed? If so, quantum mechanics is wrong at a fundamental level. Or is the information somehow encoded in the Hawking radiation in a way we don't understand? If so, how? This paradox has tortured physicists for 50 years. Recent work suggests information might be preserved through quantum entanglement between the radiation and the black hole. Or it might escape through quantum effects near the horizon. Or it might tunnel to another universe through the black hole's singularity. We don't know. We might never know. But this matters for the far future, because if information is destroyed in black holes, then everything that ever happened, every thought ever thought, every person who ever lived, all that information will be destroyed when black holes evaporate. Permanently, irrecoverably. The universe won't just become boring. It will have no memory of ever having been interesting. Let's take a step back and recognize something remarkable. We exist during the only era when the universe is complex and interesting. Before now, the universe was too hot and dense. For the first 380,000 years after the Big Bang, matter was ionized plasma. No atoms, no chemistry, no possibility for complex structures. Then atoms formed and eventually stars, but early stars had no heavy elements, no carbon, no oxygen, nothing needed for life. Those had to be forged in stellar cores and dispersed by supernovae. That took billions of years. We needed at least 2 or 3 generations of stars to create the elements for planets and biology. After now, in the far future, the universe will be too cold and empty. Stars will die. Matter will decay. Nothing complex can exist. There's a narrow window, cosmically speaking, when the universe is just right. Hot enough for nuclear reactions in stars. Cool enough for stable atoms and chemistry. Dense enough for gravity to create structures. But not so dense that everything collapses. And we're here, right now, in that window, against staggering odds. This is sometimes called the anthropic principle. We observe the universe at a time when observers can exist because observers can only exist at such times. It's selection bias. We couldn't be here at any other era. But it's still remarkable. Of all the time the universe will exist, from the Big Bang at time 0 to heat death at essentially infinite time, the era suitable for complexity spans maybe 1 trillion years. That's less than 0.001% of the universe's total timeline. We're here during the Golden Age. Some people find this knowledge depressing. If the universe will die, if everything ends in heat death, if nothing we do matters on cosmic timescales, then what's the point? Why care about anything? This is cosmic nihilism, the idea that the ultimate fate of the universe renders everything meaningless. But this reasoning is flawed. Meaning isn't something the universe gives us. Meaning is something we create. Yes, the universe will end. Yes, in 10 to the power of 100 years, nothing we do will have left any trace. But so what? Meaning operates on human timescales, not cosmic ones. Your life matters to you. Your relationships matter to the people involved. Your actions affect others in real, immediate ways. The fact that these effects won't persist for a Google years doesn't diminish them. It's like saying a beautiful song is meaningless because it ends, or a delicious meal is pointless because you'll be hungry again. Temporary things can still be meaningful. In fact, their temporariness might make them more meaningful. We have finite time. That makes how we use it important. The universe's mortality doesn't create nihilism. It creates urgency. We exist in the only era when existence is interesting. We have this brief window to experience reality, to understand it, to find or create meaning within it. That's not depressing. That's extraordinary. Could consciousness persist into the far future? Could intelligence find a way to survive heat death? Some have speculated about advanced civilizations that might slow their thinking to conserve energy, or find exotic energy sources we haven't imagined. But physics is brutally clear. Consciousness requires computation. Computation requires energy flow from high concentration to low concentration. You need a temperature difference, hot and cold. At heat death, everything is the same temperature. No gradient exists, no energy flows, no computation is possible, period. You can't build a computer that runs on nothing. You can't have thoughts without energy expenditure. Some have proposed harvesting vacuum fluctuations or using exotic physics we haven't discovered. But these are desperate hopes, not plausible solutions. Every serious analysis concludes the same thing. After the last black hole evaporates, consciousness becomes impossible. Not difficult, impossible. The universe won't contain an energy source capable of supporting even the simplest computation. A civilization that somehow survived until 10 to the power of 100 years would watch the final black hole evaporate, knowing that their existence ends moments later. Not because they'll die in any conventional sense, but because the substrate that supports their existence will vanish. You can't be conscious without energy any more than you can run a car without fuel. When the energy runs out, thinking stops. Forever. This applies to any intelligence anywhere in the universe. Aliens, if they exist, face the same physics we do. It doesn't matter how advanced they become. Technology can't defeat thermodynamics. An alien civilization a billion years more advanced than us still needs energy sources. They still generate entropy. They still face heat death. Maybe they'll last longer than us. Maybe they'll develop incredible technologies we can't imagine. Maybe they'll migrate to larger black holes and extend their existence by trillions of years. But eventually, they face the same wall. The last energy source evaporates. They can't think anymore. Game over. There's a certain democracy in this. Human, alien, artificial intelligence, uploaded consciousness, whatever form intelligence takes, all face the same ultimate limit. You cannot outlast the universe. You cannot escape entropy. The laws of physics apply equally to everyone. This should be humbling. We spend so much effort on survival and growth and expansion. We dream of becoming spacefaring species, colonizing galaxies, spreading across the cosmos. And maybe we should do these things. Maybe that's worthwhile. But in the end, it's all temporary. All of it. Every civilization that ever exists will end. Not because they made mistakes or weren't smart enough or didn't try hard enough, because physics demands it. Let me propose a thought experiment. Imagine you're the last conscious being in the universe. Through some extraordinary means, you've survived longer than seems possible. Maybe you're a digital intelligence running on a computer powered by Hawking radiation from a black hole. Maybe you've slowed your subjective time to an extreme degree. Maybe you're something we can't even conceive. But you're here, conscious, observing, and you're watching the last black hole in the observable universe. It's been your companion, your energy source, your reason for existing. You've watched it shrink year by year. Calculated how much time remains. The black hole is small now, smaller than planets, smaller than asteroids, glowing bright and hot as it radiates away its final reserves of mass energy. You know what comes next. You've known for subjective centuries. When this black hole evaporates, you die. Not might die. Will die. Certainly. There's no other black hole within reach. You've checked. You've sent probes across billions of light years. This is the last one. You watch the black hole shrink to the size of a mountain, then a building, then microscopic. The temperature is rising to unimaginable heights. The radiation is intense. You're harvesting every bit of energy you can, powering your final thoughts. What would you think about? Would you review your existence, whatever incomprehensible journey brought you here? Would you rage against the dying of the light? Would you accept the inevitable with calm resignation? Would you spend your final moments calculating precisely when the end comes? The black hole is now smaller than an atom. Temperature billions of degrees. You have seconds left, maybe less. The radiation is becoming incoherent. Your systems are failing. You can feel your consciousness fragmenting as energy supplies become erratic. Random thoughts. Memories that might not be memories. You try to hold on to something, anything, some final observation or understanding. The black hole erupts. A flash of energy. Your sensors saturate. Everything is white light and gamma rays and particle cascades. For a moment, maybe a microsecond in objective time, but an eternity in your subjective experience, you see it. The death of the last structure in the universe. The final light in an infinity of darkness. And then your power source is gone. The energy stops. Your last thought interrupts mid-formation. Consciousness ceases. Not slowly, not gradually, just stops. Like a computer being unplugged. One moment you exist, the next moment you don't. And there's no one left to know you ever existed. No one to remember. No record anywhere. You're gone, and the universe has forgotten how to care. After 10 to the power of 100 years, after the last black hole has evaporated and the last consciousness has ended, what remains? Photons. Countless photons with wavelengths stretched to absurd scales. Wavelengths larger than galaxy clusters. Larger than the observable universe once was. These photons are technically electromagnetic radiation, but calling them light seems wrong. They're so redshifted that they've become something else. Quantum excitations of the electromagnetic field stretched across cosmic distances. They'll never interact with anything. Never be absorbed or scattered or measured. They'll just propagate through expanding space forever, red-shifting continuously, wavelengths growing without limit. Neutrinos. These ghostly particles barely interacted with matter when matter existed. Now that matter is gone, they're truly alone. each neutrino traveling through space, separated from every other neutrino by distances we can't comprehend. They'll never collide, never decay, just travel, forever. A few electrons and positrons, scattered so thinly that an average volume the size of our current observable universe might contain only one particle. These particles will continue existing indefinitely, stable, solitary, irrelevant. The temperature of space itself is effectively absolute zero, maybe 10 to the power of negative 100 degrees Kelvin above true zero, cold beyond cold. No energy flows, no heat moves from place to place, perfect uniformity, and nothing happens. This is the critical point. The universe still exists, space still expands, time still passes, but nothing occurs. No events, no processes, no changes. Events require energy differences. Chemical reactions need activation energy. Particles need kinetic energy to collide. Life needs metabolism. Thought needs computation. All of these require energy gradients, hot and cold, concentrated and diffuse. When everything is uniformly spread at the same temperature, events become impossible. The universe hasn't disappeared. It's entered a state where the concept of happenings has no meaning. You could wait 1 trillion years and check back. Nothing will be different. No particles will have collided. No quantum fluctuations will have produced anything interesting. The universe will look exactly the same. Wait another 1 trillion years. Same thing. The photons have redshifted slightly more. That's it. This isn't death. Death is an event. This is stasis. Eternal, unchanging, meaningless stasis. The universe exists in a state where existence and non-existence are functionally identical. Time passes, but nothing marks its passage. Space expands, but nothing moves through it in any meaningful way. The heat death of the universe is worse than death. It's immortality without purpose, existence without meaning, forever without change. This is the ultimate fate of everything. This is where the universe is heading, and there's absolutely nothing anyone can do to stop it.